What if I told you there's a machine, an impossible machine, that could solve in mere seconds what would take the most powerful supercomputers we have today thousands of years? What if this machine didn't just follow our rules of logic, but instead mirrored the strange, almost magical rules of the universe itself? This isn't science fiction. This is the dawn of the quantum era, a time where information behaves in ways that defy our everyday common sense. We're about to explore a world that is mysterious, mind-expanding, and will fundamentally reshape our future. To understand this revolution, let's start with what we know. For over a century, our entire digital world has been built on a simple idea: the bit. A bit is like a light switch. It can either be off, which we call a 0, or it can be on, which we call a 1. Every photo you take, every message you send, every video you watch is just a long sequence of these on or off switches. Classical computers are incredibly fast at flipping these switches, one after another, to solve problems. But what if a switch could be both on and off at the same time? That's where quantum computers come in. They aren't built on bits, they're built on qubits. A qubit isn't a simple light switch. Think of it more like a dimmer knob. It can be fully off, fully on, or exist in any of the infinite states in between all at once. This mind-bending property is called superposition. Because a qubit can hold multiple values simultaneously, a quantum computer doesn't just test one solution at a time like a classical computer. It tests millions, even billions of possibilities all at once. This incredible power comes from three core principles that sound like they are straight out of a fantasy novel: superposition, entanglement, and interference. We've touched on superposition, a qubit's ability to be in multiple states at once. But then there's entanglement. This is what Albert Einstein famously called spooky action at a distance. You can link two qubits together in such a way that they become a single system. No matter how far apart you separate them, across a room or across the galaxy, measuring the state of one instantly influences the state of the other. It's a mysterious, unbreakable connection. Finally, there's interference. Just like waves in a pond can add up to create a bigger wave or cancel each other out, quantum states can interfere with one another. A quantum computer cleverly uses this principle to amplify the probability of finding the correct answer while canceling out all the wrong ones. It's like tuning reality itself to the right frequency. Together, these three principles, superposition, entanglement, and interference, create what we call the quantum advantage, the source of a quantum computer's exponential power. So, what exactly is a qubit made of? It's not one single thing. You can visualize it as a tiny spinning sphere, often called the Bloch sphere. The north pole of the sphere represents a perfect 1, the south pole represents a perfect 0, and every single point on the surface of that sphere is a valid quantum state, a mix of 0 and 1. Scientists are in a race to build the best qubit. Companies like IBM and Google use tiny superconducting circuits, cooled to temperatures colder than deep space. Others, like IonQ, trap individual atoms, ions, in electromagnetic fields and manipulate them with lasers. And some, like Xanadu, are even building qubits out of particles of light, called photons. Each method has its own strengths and weaknesses, a trade-off between stability, scalability, and how long the qubit can hold its quantum state. And that brings us to the single biggest challenge in quantum computing: decoherence. Quantum information is absurdly fragile. The slightest vibration, a tiny change in temperature, or even a stray magnetic field can cause the whole system to collapse. This collapse, called decoherence, erases the quantum information, and the qubit just becomes a boring old classical bit. Imagine trying to whisper a secret to a single delicate snowflake in the middle of a hurricane. One tiny disturbance, and your message is gone forever. This is why quantum computers are these massive, multi-million-dollar machines. The giant chandelier-like structures you see are actually super refrigerators called cryogenic chambers that cool the quantum chip down to near absolute zero, about minus 273 degrees Celsius, just to protect the qubits from the hurricane of the outside world. To solve this, scientists are working on a holy grail called quantum error correction, a way to protect the information even when noise is present. It's one of the biggest unsolved challenges standing between us and large-scale, fault-tolerant quantum computers. This challenge hasn't stopped a global quantum race from heating up. It's like the space race of the 21st century, but the finish line is a new reality of computation. You have giants like IBM Quantum, which has put its machines on the cloud for anyone to access, pioneering the use of superconducting qubits. Then there's Google's Quantum AI Lab, which famously claimed quantum supremacy in 2019 by solving a specific problem that would be practically impossible for even the fastest classical supercomputers. Startups like Rigetti, IonQ, and Xanadu are pushing the boundaries with new hardware and innovative approaches. And it's not just companies. Governments in the US, China, and Europe are pouring billions of dollars into research, recognizing that whoever masters quantum technology could gain a massive economic and strategic advantage. So what will these incredible machines actually do? It's important to know what they can and, for now, can't do. Quantum computers are not going to replace your laptop or smartphone for everyday tasks like sending emails or browsing the web. They are specialized tools for solving very specific, very hard problems. Their superpower is finding the optimal solution among a vast sea of possibilities. For example, they will be able to break most of the encryption that protects our data today by quickly factoring enormous numbers. They could revolutionize logistics by calculating the most efficient routes for thousands of delivery trucks instantly. In finance, they could optimize investment portfolios in ways we can only dream of. And perhaps most importantly, they could accelerate drug discovery and materials science by perfectly simulating molecules, allowing us to design new medicines and materials from the atom up. Quantum computers won't replace our classical machines. They'll work alongside them, tackling the problems that have always been considered unsolvable. One of the most exciting frontiers is the fusion of quantum computing and artificial intelligence. AI, especially deep learning, requires an immense amount of computational power to train models by recognizing patterns in data. Quantum computing could accelerate this training exponentially. Imagine AI models that can analyze complex systems in real time, or even simulate processes that resemble the human brain. This has led to a new field called quantum machine learning, or QML, where algorithms use principles like superposition to process data in ways that are simply impossible for classical computers. In the future, AI may not just run on quantum computers, it may begin to think in quantum logic. Of course, with great power comes great responsibility and great risks. The fact that a quantum computer could break the encryption that secures everything from our bank accounts to government secrets is a serious threat. The good news is that scientists are already on the case developing new forms of post-quantum cryptography that are resistant to attacks from both classical and quantum computers. But the implications go beyond security. They raise deep philosophical questions. If a machine can compute every possible path at once, what does the concept of a decision even mean anymore? We are stepping into an era where the speed of discovery might outpace our ability to control its consequences. So, what happens next? In the next 5 to 10 years, experts predict we will achieve quantum advantage, the point where quantum computers start solving real-world, commercially relevant problems faster and better than classical computers. Long-term, the possibilities are breathtaking. Quantum computers could simulate entire ecosystems to model climate change with perfect accuracy, design brand new materials with unbelievable properties, or even help us map the complex quantum processes happening inside our own brains. For centuries, humanity has built machines that follow our logic, that work in straight lines of zeros and ones. We taught them how to think like us. But quantum computing is different. It may be the first time we've built a machine that doesn't follow our logic, but instead mirrors the fundamental logic of nature itself, uncertain, interconnected, and beautifully complex. We are on the verge of unlocking a new language to speak to the universe, and it's a conversation that will change everything. Thank you so much for joining me on this journey into the quantum realm. If you found this as fascinating as I do, please hit that like button, subscribe for more explorations into the future, and let me know in the comments what you think the biggest impact of quantum computing will be. Until next time, stay curious.